Hello everyone, welcome back to this simple 3D renderer series. In today's episode, we will be discussing the fundamental idea of how we are going to create a 3D renderer. So without further ado, let's jump right into it. So in order to create a 3D renderer, we have to have some way of representing something in 3D because our screens are 2 dimensions. If they had 3 dimensions, then everything would be easier, but they don't. So if we want to represent 3D, we have to take a 3D object or whatever and map it to 2D. And the most commonly way we do that is using what's called a perspective projection. And it looks something like this. I just grabbed this image off the internet and I thought it was a really good representation of the perspective projection. At first glance, you'll notice a few things, but you can ignore the things I crossed off up here. These are kind of irrelevant here, but they'll kind of be discussed later. They're not really important. Um, but this, you can see again, what kind of looks to appear as a triangle prism, kind of rotated on its side, with the apex of it kind of at the origin of this three-dimensional axis. And this prism is basically going to be our perspective projection. It is going to be basically the world for which a 3D object can live in. And what's going to happen here is basically just to like give you a quick rundown is you are basically at this position here. And this near plane, spoiler alert, is going to represent our screen. And the screen is going to be a window to which anything in this prism, so let's say a tree, will be visible to us. And this will be our 3 dimensions. So anything that lives inside this prism will be mapped to a screen for which we can see. But how is that going to work? Well, to give you a quick example before we jump into the math of it, and we'll have some 3D object in space, like a triangle. This triangle will have 3 vertices, and if we were to take a vertice and draw it to the viewer, you can see that it hits this near plane at this blue point right there. And again, our near plane is our screen. This is basically the whole idea of how this perspective projection is going to work. We're going to have something in 3D, and we're going to get where it would hit or intersect this near plane and then map that to the screen. Because if we can do that, we can basically create the illusion of 3D based off of our 2 dimensional screen we have. So let's jump into how we are going to do that. But we first need to define a few things about this prism. I mentioned the near plane being our screen. And the near plane, for the most part, is our screen, but it's not directly the screen. What I mean by that is it's not just going to be a direct mapping of our screen. What's going to happen instead is we're going to define the near plane to be a simple 2 dimensional screen or axis with a positive x and a positive y and negative x and a negative y. And the max dimensions of these are going to be 1. So let's go back to what we said earlier. This triangle's vertice intersects this near plane at some point. And let's just say that that triangle intersected the near plane at about right there. And so let's just throw some random numbers at this point and say this point was at 0.8, 0, and 0.8 on the y. This point itself doesn't really have anything useful to us, right? Because if you know anything about a window or a screen, you know that it's most commonly uh, its main origin starts at the top left corner of the window, and that top left corner represents 0, 0. And the bottom right represents the max dimension and max height of the screen, so something like 800 by 600. And you can see here that this point on our near plane isn't directly close to our screen, and that's kind of why we can't just map where the triangle would hit the near plane on our screen, because if hit there, there's no way of really determining that. And yes, we could use like an offset, but it's just much more simpler to leave it as one in all dimensions in the near plane for now. But we will eventually take this point and convert it to screen. And we'll do that a little bit later in this video. But for now, that is one important thing we have to denote here. So another important thing to understand is anything that's outside of this prism, should not be drawn to the screen. Or anything that's outside of this near plane or our screen's view should not be drawn. Vice versa, anything that's past the near plane should not be drawn. Or anything that is past the far plane should not be drawn, because it's not contained in the prism, or again, our world, you can think of it as. Another important thing that we need to cover about this prism, or this perspective projection, is the field of view. You may have, if you've played a lot of first-person shooter games, you know that some games offer the option to change your field of view. And what this field of view is basically the angle of which this prism is able to be viewed. So the field of view directly relates to how much you can see in the world. So just looking at the angle we just drew there, you can see that it directly relates to this much space in the prism, or the projection perspective. But if we were to make the angle shorter, so we were to cut that in half, you can see it would lose a lot of dimension and a lot of height, and as a result, you could see less in the world. So here's our tree again. And if our tree was still up here, you wouldn't even be able to see that anymore because the field of view has changed. And so this field of view runs in both dimensions. It runs in the y and the z, and it also runs in the x and the z. So I'm going to label that the xz1 with blue here, and it kind of go that way. Hopefully you can see that. So yeah, so again, the field of view determines the amount of depth you can see, or amount you can see on the prism. The higher, the more; the lower, the less. So yeah, that's basically all the main properties of this prism we need to discuss. So now we need to figure out a way to actually take a object that's inside of the prism and map it to our near plane. And before, we kind of just estimated, right? We just kind of said that this triangle intersected the near plane at this point here. But that totally isn't accurate, right? And as a result, it wouldn't really look right if we were to draw it to our screen. So instead, we need to find a more mathematical way of doing this, because if we can, then we can more accurately draw or represent this 3D object, and as a result, we can get the expected results we want. So how do we do that? Well, I mentioned in the introduction video that you just need to have a decent understanding of trigonometry. And if you have a decent understanding of trigonometry, I promise you this won't be that hard to understand. But if you don't, I'll try to make it simple. But for now, we're just only going to look at the y and the z plane of this prism. So we're only going to focus on the y and the z. And I'm going to draw that down below. So here is our y and our z. Just change this, sorry for that. I'm also going to draw our, I'm actually going to erase it because it's not going to look right. So you may be wondering why I'm drawing the negative y here. And that is because in the prism, if you look up above, the y goes positive this way, and then the z extends into the near plane, or a screen. It intersects it right in the center. So therefore, this splits the near plane into a negative y, a positive x, a positive y, in a negative x, which I drew here before. So if I'm only focusing on the y and the z axis, I also have to include that negative y that extends down here. So again, this is just going to be a side view of this prism. So we're going to have our field of view that's going to protrude from the origin. That's going to make, again, let us determine how much we can view in this world. And then we'll have the near plane that's right here. And we don't have to worry about the far plane for now, because the near plane and what we have so far, what I have in this illustration, is the most important thing we need. And so we'll have some angle, which I'm going to get a new color for that so we can stay somewhat, let's do green. So here is our field of view angle, which I'll label with a dot and say our field of view. And our field of view for now will be 90. But if you look at this field of view, you'll notice that we can split the field of view, since we're basically running along two quadrants, that they will be basically equal, right? So these smaller lines I just drew would be half of the field of view. So these would be 45, 45 compared to a total of 90. We'll see why that's important in a moment. We also need to label our dimension of this, right? So going back up here to the near plane we drew earlier, we can see that we labeled our max dimension in each direction to be 1. Oh, yeah, so we need to label that here. So our max height of the near plane is going to be 1, and then the bottom will be -1, but still will still be 1. Notice how I did not label the length of the z. That's because this is unknown. And why is this unknown? Well, this length, again, will be different depending on our field of view. So if our field of view was more narrower, you can see that our, let's say, would look something like this. Well, it's kind of hard to draw that, but if our field of view was narrower, basically this z value or this length here would be different. So we actually have to calculate that, right? We have to determine what this length is, because right now we know that this height here is 1, but this length here is unknown. Excuse me. So how do we calculate that? Well, again, if you know simple trigonometry, you'll be able to kind of already know what to do, but if you don't, you can just follow along. We have a height here, we have an angle, and we do not know this side down here. So we have an opposite of the angle, we have our angle itself, and we want to know this adjacent. Well, what does that relate to? That relates to tangent, because we know that tangent of some theta is equal to the ratio of its opposite and its adjacent. And we can label our opposite as being 1, right? Because we know that the opposite length is already 1, and that our adjacent is unknown. So to solve for adjacent, we can just use some simple algebra, and this would equal, this would relate to the following. The adjacent would be equal to the opposite, which in this case is 1, divided by the tangent of our angle. And we also know that our angle here is going to be half of our field of view, right? Because we're only focusing on one portion of the total field of view. So we can actually break this, simplify this further into 1 over the tangent of our field of view divided by 2. And this will give us that length across the z. And again, you're probably saying, well, that's cool, but how is this going to help us? Well, remember, keep that formula remembered, because now you're going to see where it plays a part. So again, let's go back to what I said earlier. Imagine we had a triangle that lived inside of this prism, right? So let's draw that triangle again, somewhere in space. That's 3 vertices. And I said, let's imagine that we drew a line to the viewer from the vertice. So again, this origin point is still the viewer, just to clarify, and the viewer will see into the near plane, which we're only looking at the side view, so this two-dimensional view, into the world. In this case, they'll be seeing the triangle here. So, and we said that this vertice intersected our near plane at some point, which I drew in blue. Now, if we look at where this intersected this point here, this is important because, again, this represents where this 3D object would hit the screen, and you can think of it as, or where it should be represented on the screen. But we don't know exactly where it hit the screen at, right? Earlier we guessed and we said it hit 0.8 and 0.8, but that probably wasn't even close to where it actually hit. So how could we actually derive a mathematical way of where it exactly hit? Well, if you look here, you can actually see that it hit it hit right here, and if we drew that line to the viewer, we can actually see that it makes a right triangle, right? And if we look even further than that, we can actually see that the vertice of it in 3D also made a right triangle, but these are similar. So that means that their ratio or angles are going to be similar. And what that allows us to do is we actually can, using simple trigonometry, get where it hit the screen. Because again, this vertice has some x and y and z position in space. And where it hit the screen only has a y and a z, because we're only looking at the y and the z at the moment. So in that case, we don't even need to worry about the x. We only care about the y and the z. But we want to find where this hit the screen as. We want to find where it hit the y, where it hit on the screen y. And you probably say, well, why not the z? Well, if we look back into the image here, our near plane only runs across the well, it does have some depth, but it only mainly runs in the y and the x. And normally a window only has a y and x as well. So we really only care for the y here. So how are we going to find that? Well, again, we just discussed that these are going to be similar right triangles. So I'm just going to draw that now. Those are similar right triangles. So the ratios will be equal. So I'm going to label the blue as the screen Y and the screen Z, and I'm going to leave these as the Y, the Z of the object in space. So these ratios will be equal. So that means that the opposite over adjacent will be equal to the opposite and adjacent of this triangle as well. So opposite adjacent, opposite adjacent. So we can write that here. So the screen Y over the the screen Y over the screen Z will be equal to the object's Y over the object's Z. Now again, we only care about where it hit on the screen Y. So we can solve for screen Y by just using simple algebra. So multiply by the screen Z on both sides, and you'll get that the screen Y is equal to the Y position of the object in space times its times the screen Z of the intersection over the Z value of the object in space. And this right here is our formula. But wait, we're not done there because we already found out what the screen Z is. I should have said this before, but the screen Z is actually going to be the adjacent we calculated earlier. It's going to be this length right here. Right? Because earlier we were trying to find that length because we knew that the height was 1 or the opposite was 1. We knew the angle. We didn't know this length right here. We calculated it to be 1 divided by the tangent of the f by 2. So we can actually substitute that into this equation and get that the screen y is equal to the y times 1 over z times tangent of the f of v divided by 2. And this is our final equation. So what does this equation tell us? Well, it tells us that the screen location on the y, or where a object hits a screen or the near plane on the y-axis, is equal to that object's y position times 1, or in this case just the y position, divided by the z value of that object in space, multiplied by the tangent of the field of view divided by 2. So this will allow us to take an object's 3D position and get a location on the y on the screen. So that's basically it. But we're not done though. We only are looking right now at the y and the z. So therefore we're only going to get a screen y location. We also, I mentioned that we need a screen once in the x and the y. So therefore we have to do the x now. We have to get where it would hit on the screen x. So we're going to go back down and redraw our new plane. So let's draw our x and z plane. Before we saw that the y and the z created a positive y and a negative z that we were looking at. Now we're going to look at the x and the z, which is going to create a positive x and a negative x. So let's draw that. Kind of like a top-down view. So we'll have our z coming in, our x, negative x, and our z. The field of view is going to be the same as before, as we want this to stay consistent. Although my illustration probably won't be the best. And then we will have the field of view there. We'll also have our near plane right here. And we know that this length across the x here is going to be 1. So that only leaves us with one unknown, and that is this value of the z, because we have our angle and we have this value here to be 1, but this is unknown once again. So we need to calculate that. So we have a opposite, and we have an adjacent, and we have an angle. The adjacent's unknown, so that gives us tangent again. So the tangent of the angle, but we know the angle here is going to be the field of view divided by 2 is equal to opposite over adjacent. We know that our we want to solve for the adjacent, or in this case the z value. So this will be that the adjacent equals 1 divided by the tangent of the field of view divided by 2. I'm also going to just kind of put parenthesis here and just put a z. So let's go back to what we did before, and let's draw this triangle again in the space, and we'll trace the vertice to the viewer. And again, we see it hits the near plane at some point. And we want to find where this point was relative to the position of the triangle in space. So we do what we did before, and we can see that we create another similar right triangle. So again, this means that the ratios of each of those triangles will be similar. One thing to notice here is that the ratio, the length from where the viewer is to the near plane, this length right here stays the same, no matter where the object would hit the near plane. Let's say it hit it here. If we trace that, notice that the z value, or the screen z, is the same as it is here. That's why calculating this is so important, because it kind of acts as a constant but in our calculations. But again, this is dependent on the field of view of the perspective projection, because this value could change depending on the field of view value or angle. So again, we just said that these are similar, so therefore we can create a ratio of them. So this is going to give us our opposite over adjacent of the vertice in space. So in this case, we know that there's x, y, and z again, but we already found out how to get the screen y relative to the y and z. Now, so we don't need to worry about that. But now we're trying to find the screen x relative to the x and the z. So we only care about the x and z of this vertice. So our opposite over adjacent here is going to be the x over the z value of the object in space is going to be equal to the screen x of the near plane over the screen z of the near plane. And we want to find the screen x here, so just using some algebra again, we can derive that the screen x will be equal to the x of the object in space times the screen z value and divided by the z of the object in space. But again, we already found the screen z earlier, and that was the adjacent from which we calculated right here, and that was this value. So again, we can substitute that into our formula, and so we'll have screen x is equal to the x of the object in space times 1 divided by the z value of the object in space multiplied by the tangent of the field of view divided by 2. And so if we look at both of these equations here, we can see that they are very similar. Only thing that changes here is instead of, if we're looking for the y, basically the y and the z change. I mean the y and the x values of them in space change. But they are basically almost identical. So these two equations will basically allow us to, given an object in 3D, in its position in 3D space, we can then figure out where it would be within the screen space. And so, like I mentioned earlier, anything that is past the far plane or within this kind of area here, less than the near plane, or outside of the box or the prism, should not be drawn. And this will account for that. We'll see that in the next episode where we're actually going to implement this into our code. But again, if we were to have an object, I'm just going to draw this for reference. If the object was to be outside here and we traced its value to the viewer, then it wouldn't be drawn because it would not intersect the near plane, or it would be outside of the perspective projection. And we'll see that, like I said, in the next video. So that's basically going to be basically going to wrap up this introduction to the idea of how we're going to create a 3D renderer. So just to recap everything, we're going to be using what's called a perspective projection. It's going to basically represent this 3D frustum, and anything that is within this frustum will be rendered to the viewer. And we said that the viewer lies at the origin of it and looks through the near plane as a window to the 3D world that's contained inside of this. And so we defined our near plane as our screen, but we didn't define it as a screen just yet. We gave it what's actually called the normalized device coordinates. And so these range just from 1 to 1, with the origin of the coordinate system being at the center of the viewer's screen. And then we derived formulas to extract the screen Y position relative to the object's position in the perspective projection or the frustum. And we did that with simple trigonometry, and we ended with this equation here. And then we did the same thing for the x and the z, finding the screen x position relative to the x and z plane of the frustum. And we found that formula right here. So that basically wraps up this introduction to the fundamental idea. In the next episode, we will actually implement this into our code and actually begin rendering stuff. So I hope this helped anyone. Again, I apologize if my handwriting or my explanations aren't that clear. I will actually provide a few other sources in the description below for which you can watch at your own to maybe help answer some questions I didn't. But thank you guys for watching, and I will see you guys in the next one. Peace.